Let's talk about relationship problems. Just to clarify, we're not talking about problems appropriate for a couple's psychotherapy session. No, what we mean here is the relationships we might observe between different types of variables. Let's summarize with an overview of what we have seen and what we might see. If we are looking at the relationship between two scalar variables, we can look at the relationship graphically using the scatter plot or possibly the jitter plot if too many points fall on top of each other. We also introduced a summary statistic, the Pearson correlation, but we saw that this statistic should only be applied in certain settings, namely when the data follows a linear trend. Then we applied the NHST, the Null Hypothesis Statistical Test Framework, to our exploration of the relationship between two scalar variables. In particular, to assess if there is a linear relationship, we started with the null hypothesis that there is not a linear relationship. That is, h sub 0 is rho equals 0. For our discussion, I'm going to propose that instead of stating this mathematically, rho equals 0, instead, let's phrase this as there is no relationship between the variables. Again, to be precise, we should recall or clearly state that we are talking about a linear relationship, but no relationship in this case would encompass no linear relationship as well, though the direction can't be reversed there. Now we just finished the module on two independent sample t-tests. And though we didn't formally present it this way, in truth, the analyses and protocols from that discussion were all focused on the relationship between one scalar and one dichotomous variable. Recall, a dichotomous variable is one subset of the larger set of all possible categorical variables, but it has two categories or can only take one of two values. The key here, though, is that this is still just a question about whether a relationship exists or not. In our case, we have a grouping variable. The dichotomous variable indicates which group you might be in, and we have a scalar variable, the thing that we measured. And the question is whether or not there is a relationship between the values on the scalar variable for the different groups. If there is no relationship, then the average for the two groups should be the same, which means that there really aren't two groups. The distinction is artificial. Thus, there is just one big group, and thus the means should be the same. Before we go further into this alternative view of the problem, let's recall how we can visualize and analyze this type of data. Visually, we can use parallel box plots to compare graphically the groups, though we also could look at jitter plots or distributional plots like violin plots or stacked vertical mountain plots, which are just sideways histograms on either side of a shared vertical axis. As for statistics to compare the groups, one obvious choice is the difference in the group means, but this requires a sense of what a reasonable difference between the group means might be if the groups truly are not different, i.e., how spread out might random means be just by chance. What we saw was that if we convert this to a t-ratio, this is one way to standardize the difference in the group means in a fashion that would allow us to conduct an NHST. In this case, the null hypothesis was that the average for group 1 was the same as the average for group 2. But again, what does this actually mean? Well, if the averages of the two groups are the same, then any knowledge I might have as to whether you are in group 1 or group 2 gives me no useful information in predicting what your average or score might be. So again, this null hypothesis can be restated as there is no relationship between group membership and the scalar variable. Now, what do we do when we want to look at one scalar and one categorical variable, where the categorical variable has three or more categories? The statistical tool that addresses this is the ANOVA. This is the Analysis of Variance, NHST. There is an entire module on this, but we won't be focusing on this yet. So, what types of relationships remain? This is the relationship between two categorical variables, and that is the focus of this current module. We will start by looking at the relationship between two dichotomous variables. We will then extend it to looking at non-dichotomous variables. It turns out that the techniques are essentially the same. However, there is a way to look at the relationship between two dichotomous variables that does not extend well to variables with three or more categories. This instead builds off the idea of looking at proportions from two samples. Instead of focusing on this approach, we will work with the more general approach. So to visualize these relationships, we will use the Mosaic plot, also called the stacked pie graph. As for the statistic to examine the relationship in the variables, we often start with the difference in the group percentages or ratios. So in this framework, we would present the hypothesis as H sub 0, the null hypothesis, is that the percentage for group 1 is the same as the percentage for group 2. Now at this point, we must carefully dissect how we are thinking about our variables. In this case, we are using one of the dichotomous variables as a grouping variable, group 1 and group 2. And then we are using the other dichotomous variable as the variable to ascertain the proportion of times a successful observation is actually observed in each group, the success versus failure variable, if you will. Let's unpack this a bit more with a context. Let's say our first variable is sex, male versus female, and let's say our second variable is the presence of a particular genetic marker. If you have the genetic marker, that would be coded in the data as a 1, and if you don't have the marker, that would be coded as a 0. Next, we can ask what percentage of the males from the sample have the genetic marker, and what percentage of the females from the sample have the genetic marker. The p in this null hypothesis is referring to the percentage of the genetic marker, and the 1 and 2 are referring to the sex groupings observed in this dataset. Once again, if these percentages are the same, that would suggest that there is no relationship. In this case, there is no relationship in the frequency of the occurrence of the genetic marker for males versus females. More generally, there is no relationship between the grouping variable and the percentage of times a successful outcome is observed. The percentage of success is in reference to a successful observation of that thing for which we are looking. Recall, it is not a value statement about that thing being quote-unquote good or quote-unquote bad. While our examination of different percentages could possibly be extended to scenarios where we have a grouping variable with 3 or more groups and a second dichotomous variable that can be treated as a success versus failure variable, even here the analysis of the difference in percentages becomes problematic. We will explore why shortly, but once we are looking at 2 categorical variables, each with 3 or more categories, this percentage comparison framework falls apart completely. Consequently, we will use a different comparison technique, and this is the chi-square test. This is what we will work to build up in our current discussion. Let's dive into a problem. Here's our research question. Is there an observable difference in the frequency and/or presence of a particular fracture pattern for bones exposed to different types of torsion damage? This will be the guiding research question for our current discussion. I'll provide a very brief explanation for the context of this research. When forensic scientists are working with homicide detectives investigating infant deaths, there are often different types of fractures that are found on non-fully formed bones, and different types of trauma events, e.g. shaking or yanking or twisting, etc. These different types of trauma events often result in different types of fracture patterns. The data presented here is just a simulated data set, but it is modeled after an authentic research project conducted by researchers with which I have worked in the past. So let's turn this into a claim. We'll start with a non-directional claim, though in truth we have reason from past experience and physical laws to suggest a directional claim. Essentially, we expect more of the particular bone fracture pattern for non-fully formed bones when exposed to high torsion trauma as opposed to low torsion trauma. The idea of yanking something versus yanking and twisting at the same time. But again, we will claim that the proportion of bones showing the fracture pattern is not the same, is different, i.e. not equal, for bones exposed to high versus low torsion trauma. Again, we have justification for a directional claim, a one-tailed test, but we will start here with the more general, the more conservative claim that there simply is some difference, a two-tailed test. To convert this to a pair of hypotheses, we will start with P being the percentage of bones showing the fracture pattern. This would be variable 1, the fracture pattern is present or not. Variable 2 would be the level of torsion in the trauma, high or low torsion, the grouping variable, if you will. So we have P sub H for the percent for the high torsion group, and P sub L for the percent for the low torsion group. And our claim is that these two percentages are not going to be the same. P sub H does not equal P sub L. To reiterate, the percentage of high torsion bones showing the bone fracture pattern is not the same as the percentage of low torsion bones showing the bone fracture pattern. Because this expression does not contain an aspect of equality, this would become the alternative hypothesis for our NHST. And thus, the null would be the exact opposite, or H sub 0 is P sub H equals P sub L, where the exact opposite of not equal is equal. So now let's look at the data. For our variables, we have the fracture pattern. Was the fracture pattern present or not? The second variable is the torsion, and we have low torsion and high torsion. From our data, we had 8 high torsion trauma instances that did not show the fracture pattern, and we had 27 high torsion trauma incidences that did show the fracture pattern. Whereas for the low torsion trauma, there were 15 that did not show the fracture pattern and 13 that did. You probably recall from an earlier module in the term that this is a contingency table, and this is technically not the actual data. Instead, it is just a summary of the data. For this summary, we can obtain the marginal frequencies, i.e., how often did each value for each variable show up in the data set, and we can obtain the total sample size. But again, this is a summary, not the actual data. What would the raw data actually look like? Or what might you expect to see in the Excel sheet that stores the original data? Well, we would expect there to be 2 columns in our data set. One column would be for the variable fracture pattern, and the values in this column would be yes or no, or present versus not, as in yes, the fracture pattern was observed, or no, the fracture pattern was not observed. The other column would be for the type of torsion applied to the pig fetus. The values in this column would be low or high torsion, and each row would represent a different experiment with a different pig fetus. Now, the ordering will be different, but we would expect to find 15 rows that indicate there was no fracture pattern observed and the torsion was low, like the second row shown here. Of course, we wouldn't expect the data to be ordered or sorted in a manner where all of these 15 rows are right next to each other, at least not necessarily from the raw data as it is entered into the Excel sheet, because there would be a bit more randomness as the data is coming in. And each row would be filled out one after the other for each time the experiment is run. This will prove important because this helps us to see the bivariate nature of the data, and this suggests how we might shuffle the data to simulate quote-unquote no relationship. Unlike when we are looking at a correlation to understand if there is a relationship, here we are using the first column's variable to determine which group we are in, but the idea is still the same. We are looking at 2 variables, and we want to know if there is a relationship. So that is how we summarize the overall data. Now let's look at how we might graphically represent this. Let's look at a mosaic plot, also sometimes called a stacked pie chart. If I'm focusing on the level of torsion in the trauma, this upper row represents the low torsion data. The second row represents the high torsion group. You will probably note that the row heights are different because each height is proportional to the amount of data in each group, but each bar is broken respectively as a pie chart might have been. From these horizontal pie charts, if you will, you can get a sense of what proportion showed the fracture pattern or not. The lighter golden rectangles are for those that show the fracture pattern, and the darker orange rectangles are for those that did not show the fracture pattern. Again, we call this a mosaic plot, or what I call a stacked pie chart. Now, what's the difference between these 2 plots? Quantitatively, there is no difference. It is the same data being used in both plots. But qualitatively, there is a difference. In the first plot on the right, the grouping variable was the type of torsion trauma. The grouping variable in the second mosaic plot on the left is whether the fracture pattern was present or not. The left column are all the bones not showing the fracture pattern, and the right column are all the bones showing the fracture pattern. But here, the horizontal bars breaking up each column are showing what proportion of those bones were exposed to high versus low torsion. So what in the world is this third plot? I jokingly call these even split plots the Nordic-flag-like plot. This cross-like feature, an even split by row and column, what this feature shows is what an equal split would look like if what you had was the same overall proportions in the rows and the same proportions in the columns. In other words, what would it look like if the probability of success was the same in each group, and you have the same number for each of the values for your observed variables. In our case, this is what it would look like if the same proportion of bones showing the fracture type occurred for the different levels of torsion. Everything essentially lines up perfectly. Curiously, this third plot is actually the graphical representation of the null hypothesis. So if this is the null hypothesis, and if this is what our data looks like, then we can hypothetically imagine what might our data look like if we started shuffling our data and regenerating similar plots, or summarizing in similar contingency tables, or calculating similar test statistics. The thing to keep in mind is that the horizontal bar will remain the same regardless of how we shuffle our data. What will change by random chance is where the vertical splits fall for each of these two horizontal groupings. Now, if we look at these three plots together, where the outer two plots emanate from this first even split plot, what we see is that with our data, we can either draw the horizontal bar in the same spot, but the vertical splits in the groups change, or we can draw the vertical bar in the same spot, but the horizontal splits in those groups change. Either way, the question for us to ponder is if the observed split in our actual data deviates so far from what a split that occurs from chance assignment might look like. The mathematical or probabilistic idea governing what we are doing here is that we are forcing the marginal percentages or our marginal frequencies to be the same for our hypotheses as we observed in our data. And in turn, our simulated data will have the same marginal frequencies. Only the relationship between the variables is being changed. What is free to change by some random process is the actual counts in the contingency table, as long as the marginal totals are the same. And this is what leads to the degrees of freedom, but we'll talk more on this shortly. This follows from the idea of shuffling our data. Regardless of how we shuffle, the rows within each column, the total number of any one value in that variable remains the same. That is, the marginal frequencies remain unchanged when shuffled. The only thing the shuffling process will do is mix up the connections between the values for each variable. And this is how we simulate no relationship between our variables. So let's run the simulation to see what might happen by chance. What we will do is shuffle the data. Remember, the data is what is recorded in the Excel sheet, the bivariate data appearing in n equals 63 rows and 2 columns. The data is not the summary reported in the contingency table. If we shuffle the data in those 2 columns, the total number for each of the high and low torsion experiments won't change, and the total number for each of the presence of the fracture types won't change. What will change is the association between them. And if we are doing the shuffling randomly, there is a random assignment. Random assignment means there is no relationship between the two variables. Let's run it a few times. To clarify, what we are doing after we shuffle the data is to calculate the percentage of each of the torsion types, high versus low, that show the presence of the fracture pattern or not. Once we have the percentage success, the presence of the fracture type, for each group, we will subtract those percentages in some predetermined order, in this case, high torsion percent minus low torsion percent. Then we repeat the process again and again and again and again. Once we have thousands of simulations, we can plot the test statistic from each simulation. And here's the histogram for one such simulation run 4,000 times. Now we will ask, how often do we observe our sample statistic, that's the thick vertical red line here, compared to the rest of the simulations? Graphically, it appears that our value doesn't show up that often. In fact, here it, or something larger, appeared only 52 out of 4,000 times. Note, because we are doing a two-tailed null hypothesis statistical test, we need to ask how many equally extreme results are on the negative side of the distribution as well. This would be everything below the dashed line. So our estimated p-value would be the percent of simulations that fall beyond these two vertical lines. In this simulation, that was 75 out of 4,000, or about 1.9% of the simulations. So let's get a sense of where we are going with this. While this percentage difference is probably the easiest test statistic we could calculate and interpret in a shuffling simulation like this, it turns out there is a better test statistic to use. This is the chi-squared test statistic, and we will be looking at this shortly. Briefly, we will see that the chi-square is something akin to the square of the differences between the group proportions. As a consequence, all of the negative differences become positive, and we end up with a right-skewed distribution. And to date, we haven't spent much time working with skewed distributions in this class. The simulation counts remain the same. There are 75 out of 4,000 simulated chi-square statistics that were the same or larger than our observed value. Fortunately, the NHST-framework still follows as before. The definition and interpretation of the p-value is the same as before, and the ability to interpret the simulation is the same as before. The same structure and interpretation is driving our assessment of our data as evidence. Here is our observed data, here is what we might expect by chance, and we can see how often we would encounter an observation like ours, or one more extreme, under the null hypothesis, under the assumption of no relationship, that is. It turns out the p-value from this simulation is about 1.9%, and the actual analysis gives a p-value of about 1.2%. So the probability of observing my sample or something more extreme is just a bit over 1%. A significance level of alpha equals 0.05 or 0.02 would lead to the decision to reject the null, since p is less than alpha. However, if alpha was 0.01, the conclusion of the test would go the other way. And this is why it is important to set the standard for your decision-making process well in advance. Now, if we do reject the null in this context, that means we reject the assumption that the variables are not related to each other. If we reject this, we are essentially saying that the variables are related to each other. So the conclusion, restated, would be that the sample evidence supports the claim that the proportion of bones showing the fracture pattern is different for low versus high torsion trauma. In the next presentation, we'll break down the process of the chi-squared test statistic.